Welcome to the Deep Dive, where we plunge into the fascinating world of knowledge, turning complex information into clear insights.
Hello.
Today we're embarking on a deep dive into the incredible realm of aromatic heterocycles. Now, you might not know them by name, but these compounds are, well, they're everywhere.
Absolutely everywhere. They have a huge impact on our daily lives.
Think about it. From life-saving drugs like quinine, battling malaria for centuries, to modern things like Viagra, even the building blocks of our DNA and RNA.
And flavors in food, too. It's kind of amazing.
It really is. So many significant organic compounds for us humans fall into this class.
It's a massive group of molecules, maybe, what, 2/3 of all known organic compounds?
Yeah.
Their impact on medicine is just undeniable. We're talking things like the first effective antibiotic, sulfapyridine, back in 1938.
Right, and those blockbuster anti-ulcer drugs like Tagamet in the 70s.
Exactly. These aren't just, obscure things sitting in a lab. They're foundational to chemistry and medicine today.
Definitely. So our deep dive today is primarily based on Chapter 29, Aromatic Heterocycles 1, Reactions, from Clayden, Greeves, and Warren's Organic Chemistry, 2nd edition.
Great textbook.
Our goal here is to quickly but thoroughly unpack the principles governing these compounds. We really want to get into how their structures dictate reactivity.
And crucially, how chemists use that knowledge, for clever synthesis strategies, functional group transformations, that kind of thing.
We'll be focusing on the why behind their behavior, exploring reaction pathways, and looking at the, ingenious ways these molecules get built or modified.
Consider this your fast track to understanding one of organic chemistry's most vital families.
Okay, so where do we start? Let's begin with a real classic, pyridine. It's a 6-membered ring, contains a nitrogen atom.
Right. You can basically think of it as benzene, but swap out one CH group for a nitrogen.
And it's still aromatic, just like benzene.
It is. It keeps that stable, delocalized system, the 6 pi electrons. The nitrogen fits right in. It's trigonal, has a orbital contributing, stays flat, conjugated.
So it holds on to that special aromatic stability.
It does. What's interesting is that pyridine is essentially a stable aromatic immuning. Most immunes are super reactive intermediates, right?
Yeah, they don't usually hang around.
But pyridine does. It's also a weak base.
Yeah.
Its conjugate acid has a pKa around 5.5. So much weaker than your typical saturated immuning.
But still a decent nucleophile. I see it used in catalysis a lot.
Oh, yes, especially with carbonyl groups. It's a common nucleophilic catalyst in acylations, helps transfer those acyl groups.
And this is where that key detail about the lone pair comes in, isn't it?
Exactly. The nitrogen lone pair in pyridine, it's not part of that aromatic pi system. It sits in an sp2 orbital pointing outwards, orthogonal to the ring's p orbitals.
Ah, so it's available.
It's available. Ready to grab a proton, which makes pyridine basic, or attack something electron deficient, making it nucleophilic. That distinction is really fundamental to understanding its chemistry.
And that leads to things like DMA, right? And dimethylaminopyridine. That's like pyridine on steroids for catalysis.
Pretty much. It's an even better acylation catalyst. That extra amino group pushes electron density towards the ring nitrogen, boosting its nucleophilicity, makes it super efficient.
A small tweak, big difference.
It really shows how structure tuning works. Okay, so let's dig into pyridine's reactivity. How does that nitrogen affect the ring itself?
Well, nitrogen's more electronegative than carbon, so it pulls electron density away.
Precisely. It pulls electrons towards itself, making the whole ring less electron-rich, more electron-poor compared to benzene.
So standard electrophilic aromatic substitutions like nitration or Friedel-Crafts, pyridine isn't keen on those.
Not at all. It's a very reluctant partner. The ring's just too electron-poor to react easily with electrophiles, which are looking for electrons.
And there's that practical issue too, right? The acidic reagents just protonate the nitrogen.
That's the other killer. Strong acids, Lewis acids, they just grab onto that lone pair, forming a pyridinium ion or a complex, and that positive charge makes the ring even more deactivated, totally unreactive towards electrophiles.
So forget about typical EAS on simple pyridines.
Pretty much. The nitrogen also destabilizes any positive charge that might form in an intermediate during electrophilic attack. It's just uphill all the way.
But, and this is the fascinating contrast, while it's terrible for electrophilic substitution,
it's surprisingly good at nucleophilic substitution, especially at the 2 and 4 positions.
the opposite situation.
Exactly. That electronegative nitrogen, the thing that makes it electron poor, actually helps stabilize the negative charge that forms when a nucleophile attacks the ring. It kind of acts like a carbonyl group in that respect.
So it facilitates the attack.
Right. It lowers the energy of the LMO, makes it easier for nucleophiles to come in. This lets you replace things like halogens with anamines or thiolates relatively easily.
Like in that fluprotein synthesis example, the analgesic.
That's a great real-world case. It involves exactly that kind of nucleophilic substitution on a 2-methoxypyridine.
And those starting materials, the chlorpyridines, often come from pyridones. Tell me about those.
Ugh. Pyridones. They're interesting because of tautomerism. If you have 2-hydroxypyridine, it looks like a phenol, right?
Yeah.
But it actually prefers to exist as 2-pyridone, that's the amamide form, with a CuO double bond.
Why the preference?
It comes down to bond energies and aromaticity. You get a really strong CO bond, and the ring system still retains its aromatic character. So the pyridone form wins out thermodynamically.
And that pyridone is then useful synthetically.
Very. You can treat it with something like phosphorus oxychloride, POCl3, and convert that CO group into a CCl bond. You get a 2-chlorpyridine.
Just like making an acetyl chloride from a carboxylic acid.
Exactly analogous. It's a key functional group transformation.
Okay, so what if you absolutely must do an electrophilic substitution on pyridine?
Yeah.
You mentioned a workaround. N-oxides.
Ah, yes, the N-oxide trick. This is really quite ingenious. You take pyridine, oxidize it with something like MCPBA, and you get pyridine N-oxide.
What does that do?
It's a stable dipolar molecule. Now, the oxygen atom, which has a formal negative charge, can actually push electron density back into the ring via resonance.
So it activates the ring?
It activates it for electrophilic attack, particularly at the 4 position and also the 2 position to some extent. It overcomes that initial deactivation.
But wait, you said it enables nucleophilic substitution too. How does that work?
That's the really clever part. The nitrogen in the N-oxide has a formal positive charge, which still makes the ring susceptible to nucleophiles. And the oxygen itself. You can treat it with PCl3, phosphorus trichloride, and it becomes a good leaving group.
Wow, so it facilitates both.
Dual reactivity. It's incredibly powerful. You see it used, for instance, in making nicotinic acid derivatives. PCl3 can activate the N-oxide and a carboxylic acid at the same time, leading to chlorination, then nucleophilic displacement.
And then you just take the oxygen off again.
Yep. Once you've done the reactions you need, you can just reduce the N-oxide back to pyridine using a trivalent phosphorus compound, like PPH3. It's like a temporary modification to completely switch the ring's reactivity profile.
That's really elegant. Controls everything in synthesis.
Absolutely. And pyridine isn't just a building block, it's also a catalyst and reagent itself.
Like in bromination.
Right. It can catalyze the bromination of benzene. Pyridine attacks bromine to form an N-bromopyridinium ion. This intermediate is actually a better source of electrophilic bromine than Br2 itself. Pyridine acts as a nucleophilic catalyst in a leaving group.
And you mentioned safer solid reagents.
Yes, pyridamine tribromide. It's a solid, much easier and safer to handle than liquid bromine, but delivers bromine effectively.
And for oxidation, PCC and PDC.
Pyridinium chlorochromate and pyridinium dichromate. These are milder, less acidic chromium reagents. They're great for oxidizing primary alcohols just to the aldehyde stage, stopping before they go all the way to carboxylic acids. Gives you more control.
Very useful. And metal complexation. By P.
Bipyridyl or bi-P. That's essentially 2 pyridine rings joined together. It acts as a bidentate ligand, meaning it can grab onto a metal ion with both nitrogens. It's a really common and important ligand for transition metals like iron 2, used in catalysis and materials.
Okay, so that gives us a good handle on pyridine, the 6-membered nitrogen heterocycle. Now let's switch gears. What about the 5-membered rings? Pyrrole, furan, thiophene. You said pyrrole is almost the opposite of pyridine in some way.
In terms of electron distribution and reactivity, yes, it's fundamentally different. Remember how pyridine's lone pair was outside the aromatic system?
Yeah, and that sp2 orbital.
Well, in pyrrole, the nitrogen's lone pair is part of the aromatic sextet. It's fully delocalized inside the ring system, contributing 2 electrons to make up the 6 pi electrons needed for aromaticity.
Oh, so that makes the ring itself electron-rich.
Exactly. Much more electron-rich than benzene. And because that lone pair is tied up in aromaticity, the nitrogen itself is hardly basic at all. Its conjugate acid has a pKa around -4. It really doesn't want to be protonated on the nitrogen.
If you do protonate it, it goes on carbon instead.
Usually, yes. Which can lead to problems, as we'll see.
But here's the twist. While the nitrogen isn't basic, the NH proton is quite acidic.
Surprisingly acidic. pKa around 16.5, similar to an alcohol. When you remove that proton, the resulting pyrrole anion is aromatic and very stable, kind of like the cyclopentadenyl anion.
Okay, so electron-rich ring. That means it loves electrophilic substitution.
Loves it. Much more readily than benzene. In fact, it's often too reactive. If you try something like bromination, you can easily get substitution at all available positions.
Polysubstitution.
Right. And the other problem is strong acids. Because protonation happens on a carbon, not the nitrogen, it breaks the aromaticity and forms a reactive intermediate that can easily polymerize. So strong acids are generally bad news for pyrrole.
So you need milder conditions, controlled reactions.
Definitely. Things like the Vilsmeier reaction, which puts an aldehyde group on, or the Mannich reaction adding an aminomethyl group. These use less aggressive electrophiles and work well.
And where does the substitution usually happen? The 2 and 5 positions?
Typically, yes. The 2 or 5 positions are preferred over the 3 or 4.
Why is that? What's the mechanistic reason?
It comes down to the stability of the intermediate commation, the Wieland intermediate. When the electrophile attacks at C2, the positive charge can be delocalized over 3 atoms, including the nitrogen, in a nice linear conjugated system. Attack at C3 leads to a less stable cross-conjugated system where the charge is only delocalized over 2 carbons.
So the C2 attack intermediate is just more stable.
Much more stable. For complex syntheses where you need specific regiochemistry, chemists sometimes use temporary blocking groups, maybe an ester, to force reaction at a different position and then remove the blocker later.
Clever. And since the NH is acidic, you can deprotonate it.
Yes, you can easily form the pyrrole anion, and that anion is a great nucleophile, reacting cleanly with electrophiles at the nitrogen.
So you can N-acylate it, for example.
Exactly. Making N-bacapyrrole is a standard reaction, often using DMP as a base to help deprotonate and catalyze the reaction.
Okay, so that's pyrrole. What about its cousins, furan and thiophene? Oxygen and sulfur instead of nitrogen.
Right. They also undergo electrophilic aromatic substitution pretty easily because the oxygen or sulfur lone pairs also contribute to the aromatic system, making the rings electron-rich.
Are they as reactive as pyrrole?
Generally, no. The reactivity trend goes pyrrole N is the most reactive, then furan O, then thiophene S. Thiophene's reactivity is actually quite close to benzene's.
Why the difference?
It's about orbital overlap. Nitrogen's 2p orbitals overlap very effectively with carbon's 2p orbitals. Oxygen's 2p are a bit less effective, and sulfur's larger 3p orbitals overlap even less well with carbon's 2p. So the electron donation into the ring decreases as you go from N to O to S.
Makes sense. Do they do Friedel-Crafts?
They do, but again, usually with less reactive acylating agents like anhydrides and milder Lewis acids compared to benzene. And regioselectivity usually favors the 2 or 5 position, just like pyrrole.
Now, furan has some unique behavior, right?
Yeah,
Addition reactions.
Yes. This is really interesting. Furan is the least aromatic of the 3. So sometimes, instead of just substitution, it can undergo electrophilic addition.
Like an alkene.
Sort of. A classic example is reacting furan with bromine in methanol. Instead of substitution, you get 1-4 addition across the ring. Methanol acts as a nucleophile to trap the intermediate cation, forming a stable 1-4 acetyl.
And that acetyl can be hydrolyzed.
Right. Hydrolysis gives you a 1-4 dicarbonyl compound, cis-butanediol, although it's often unstable.
So furan can be seen as a sort of masked 1-4 diketone.
Exactly. It's a fantastic retrosynthetic trick. If you need a 1-4 diketone, maybe making a furan first and then unmasking it later is the way to go.
Clever. What about thiophene? Any special tricks?
Thiophene has its own unique reaction, reductive desulfurization. If you treat thiophene with rainy nickel, which is finely divided nickel saturated with hydrogen, it rips the sulfur atom right out of the ring.
And what do you get?
You get a straight saturated 4-carbon chain. If you acylate the thiophene first at the 2 and 5 positions and then do the rainy nickel reduction, you can end up with a 1-pass and 6 diketone. So another route to diketones, but different connectivity than from furan.
And both furan and thiophene can be metallated, lithiated.
Yes, they undergo directed orthometallation really well. The oxygen, or sulfur heteroatom, activates the CH bond right next door, the 2 position, towards deprotonation by strong bases like butylithium, bulili.
Forming an organolithium compound.
Right, a highly reactive nucleophile at the position. You can then react that with all sorts of electrophiles, aldehydes, ketones, alcoholides, CO2, to install substituents specifically at that position.
And those products can be useful intermediates themselves.
Definitely. You can hydrolyze furan derivatives made this way to get 1,4-dicarbonyls, or sometimes cyclize them to form new rings like cyclopentanones. Very versatile chemistry.
Okay, one more really distinct reaction type for these 5-membered rings.
Yeah.
Diels-Alder. Benzene doesn't do that.
That's right. Diels-Alder reactions are generally off-limits for benzene because it would mean losing too much aromatic stabilization energy. But these 5-membered heterocycles, especially furan, are much better participants.
So furan acts as the dino.
Yep. It reacts readily with electron-efficient dinophiles to form a bicyclic adduct with a new 6-membered ring. It's a paracyclic reaction.
Is there anything tricky about it?
One interesting point is stereochemistry. Because the reaction is often reversible with furan, you tend to get the thermodynamically more stable exoadduct rather than the kinetically preferred endoadduct you might expect based on secondary orbital interactions. Something to keep in mind.
And thiophene. Does it do Diels-Alder?
Thiophene itself, being more aromatic, is generally reluctant. But here's another clever trick. If you oxidize thiophene to thiophene dioxide, the sulfone, you destroy the aromaticity. The sulfur lone pairs are now tied up bonding to oxygen.
So the sulfone isn't aromatic anymore?
Correct. And that thiophene sulfone undergoes Diels-Alder reactions quite nicely. And what's really neat is that the resulting bicyclic adduct readily loses sulfur dioxide, SO2 gas.
Leaving behind.
A new substituted 6-membered ring, often a benzene derivative. It's a fantastic way to build substituted aromatics starting from a thiophene. You see similar things with alpha pyrons losing CO2 after a Diels-Alder.
Wow, these heterocycles have a lot of tricks up their sleeves. Okay, let's broaden the scope. What about rings with multiple nitrogens or fused systems, starting with 5-membered rings like imidazole?
Right. Imidazole and its isomer pyrazole both have 2 nitrogens in a 5-membered ring. The key thing to grasp is how the nitrogens share roles. One nitrogen acts like the nitrogen in pyrrole. Its lone pair is in the aromatic pi system.
Contributing 2 electrons.
Yes. The other nitrogen acts like the one in pyridine. It replaces a CH group, contributes 1 electron to the pi system, and its lone pair sits outside the ring in an sp2 orbital.
So one is pyrrole-like, one is pyridine-like.
Exactly. And this gives imidazole some really fascinating properties. It's amphoteric.
Meaning it can act as both an acid and a base.
Yes, and it's actually a stronger base than pyridine, and its NH proton is more acidic than pyrroles. The imidazolium ion, the protonated form, has a pK of about 7.
Right around neutral pH.
Precisely. This makes it incredibly important biologically. The imidazole ring is the side chain of the amino acid histidine. It's perfectly tuned to act as a proton donor or acceptor, or as a nucleophile under physiological conditions. It's a key player in many enzyme active sites.
And in the lab, as a catalyst.
Yes, it's often used as a nucleophilic catalyst, for example, in putting silly protecting groups onto alcohol. It helps shuttle the silly group.
And that reagent, CDI, carbonyl dimidazole.
Ah, CDI, a really useful reagent. It's basically phosgene, COCl2, but with the chlorines replaced by imidazole groups. Phosgene is horribly toxic gas. CDI is a stable solid, much safer to handle.
And it does the same job, linking things with a carbonyl.
Pretty much. It reacts with nucleophiles like alcohols or amines. The first nucleophile adds, kicking out 1 imidazole. Then a second nucleophile comes in, kicking out the other imidazole, which is a great leaving group. It's a controlled way to form esters, amides, carbonates, etc.
Neat. What about tautomerism in imidazole?
It undergoes rapid proton transfer between the 2 nitrogens. This means that if you try to do an electrophilic substitution, like nitration, you often get a mixture of products because the electrophile might see either tautomer. You see this in the synthesis of metronidazole, the antiparasitic drug.
Okay, beyond imidazole, there are triazoles, 3 nitrogens.
Yep, 1-2-emitter-3-triazole and 1-2-emitter-4-triazole. The 1-1-4 isomer is particularly important these days. It's the core structure in many modern agricultural fungicides and also human antifungal drugs like fluconazole.
Why it's so useful?
Well, it's very stable, and the extra nitrogens make the NH proton even more acidic than an imidazole. So it's easy to form the anion, which can then react as a nucleophile, for instance, opening epoxides during synthesis.
And then tetrazole, 4 nitrogens, 1 carbon.
Tetrazole is really pushing the nitrogen content, and it's remarkably acidic. The NH proton has a pKa around 5, similar to a carboxylic acid.
Wow, why so acidic?
Because the negative charge in the resulting anion is delocalized over all 4 nitrogen atoms. That's a lot of stabilization.
And that acidity makes it useful in drug design.
Absolutely. It's often used as a biosostere for a carboxylic acid group.
A what?
A biosostere, basically, a different functional group that has similar size, shape, and electronic properties, so it can mimic the original group in a biological context. Sometimes replacing a carboxylic acid with a tetrazole group can improve a drug's properties, maybe its absorption or metabolic stability, like in some versions of the anti-inflammatory drug indomethacin.
Interesting. But you mentioned a potential downside, explosiveness.
Yeah, a word of caution. Compounds with lots of adjacent nitrogen atoms, especially chains or rings of them, can be energetically unstable, meaning potentially explosive. Tetrazoles themselves are usually okay, but derivatives like diazotetrazole are known energetic materials. It's something chemists working in this area have to be very aware of.
Good to know. Okay, let's move to benzo-fused systems. Pyrrole fused to benzene gives indole.
That's right. Indoles are incredibly important structures. You find them in the amino acid tryptophan, in neurotransmitters like serotonin, in drugs like indomethacin again, and in some pretty potent natural products like LSD and strychnine.
So how does the fusion affect the chemistry? Is it like pyrrole or like benzene?
It's mostly like a very reactive pyrrole ring fused to a relatively unreactive benzene ring.
Yeah.
The action usually happens on the 5-membered pyrrole part.
And where does electrophilic substitution occur? You said pyrrole likes the 2 position, but indole.
Indole almost always reacts at the 3 position. It's the opposite preference to pyrrole itself.
Why the switch?
It's all about maintaining the aromaticity of that fused benzene ring. If attack happens at C3, the intermediate cation keeps the benzene ring fully aromatic. The positive charge is handled within what looks like an isolated enamine system in the 5-membered ring part.
Okay.
But if attack happened at C2, the intermediate would have to disrupt the benzene ring's aromaticity significantly to delocalize the charge. That's much less favorable energetically.
So C3 attack keeps the benzene ring happy.
Essentially, yes. You see this preference consistently in reactions like Vilsmeier formulation or the manic reaction on indoles. They go cleanly to the 3 position.
Got it. What about HOBT? 1-hydroxybenzotriazole. That comes up in peptide synthesis.
Ah, HOBT. A lifesaver in peptide coupling. When you're joining amino acids together using coupling reagents like DCC, there's a risk of racemization losing the stereochemical purity at the chiral center of the amino acid being activated.
Which is bad for the final peptide's function.
Very bad. HOB helps prevent this. It acts as an additive. It quickly intercepts the highly reactive intermediate formed by DCC, creating a less reactive HOB ester. This intermediate is much less prone to racemization, but is still reactive enough to be attacked by the next amino acid's immunome group.
So it acts like a stabilizing placeholder.
A very effective one.
Yeah.
It's a standard component in many modern peptide coupling protocols.
Okay, shifting to fused 6-membered rings now. Pyridazine, pyrimidine, pyrazine. These have 2 nitrogens in a 6-membered ring, fused or not.
Right. Unlike pyridine, these diazines are all very weak bases because the second electron withdrawing nitrogen further lowers the basicity. Their chemistry is really dominated by nucleophilic attack, especially if there are good leaving groups like halogens attached.
So similar to pyridine's nucleophilic substitution, but maybe even more reactive.
Often, yes. For example, if you have 2-3-dichlorpyridazine, you can displace the chlorines one by one with a nucleophile like an amine. Interestingly, the first displacement is usually faster than the second.
Why is that?
Because once you replace an electron-withdrawing chlorine with an electron-donating amino group, the ring becomes less electron-deficient overall. This makes the rate-determining addition step for the second nucleophilic attack slower.
Makes sense. Then we have quinolines and isoquinolines benzene fused to pyridine.
Right. Here, the chemistry is a mix. You've got both a benzene-like ring and a pyridine-like ring fused together.
So where do reactions happen?
It depends on the reaction type. Electrophilic substitution, like nitration, prefers the electron-rich benzene ring, typically giving substitution at the 5 and 8 positions, avoiding the pyridine ring.
And nucleophilic substitution.
That favors the electron-poor pyridine ring, especially if you activate it by forming the N-oxide first, similar to pyridine itself. You can also do quite drastic things, like vigorous oxidation, which can actually chew away the benzene ring entirely, leaving you with a pyridine dicarboxylic acid.
Interesting. And sometimes the nitrogen is right at the fusion point. Indolizine.
Indolazine is a good example. Nitrogen is part of both the 5- and 6-membered rings. It forms a 10-pi-electron aromatic system around the periphery. It tends to react with electrophiles on the 5-membered ring part.
And purines, fused imidazole and pyrimidine rings. Super important biologically.
Absolutely fundamental. Adenine and guanine, 2 of the bases in DNA and RNA, are purines.
And caffeine is a purine too, right?
It is a methylated xanthine derivative. Uric acid involved in gout is also a purine. And the drug allopurinol, used to treat gout, is an isomer of hypoxanthine. It mimics a natural purine to inhibit the enzyme xanthine oxidase.
Even the smell of roast meat has a fused pyrazine involved.
Apparently so. The Maillard reaction produces all sorts of complex heterocyclic compounds.
Okay, nearly there. What about rings with nitrogen and other heteroatoms like oxygen or sulfur? Oxazoles, thiozoles.
These are 5-membered aromatic rings containing nitrogen and either oxygen, oxazole, or sulfur, thiazole. Unlike nitrogen, neutral oxygen or sulfur typically only forms 2 bonds in these stable aromatic systems, so they behave more like the pyrrole nitrogen, donating a lone pair to the pi system.
So you usually only find 1 oxygen or sulfur per ring.
In the common stable ones, yes. The isoisomers, like isoxazole or isothiazole, where you have an NO or NS bond, tend to be less stable. Those weak heteroatom bonds can sometimes be cleaved, for instance, by reducing agents.
Any drug examples?
Sure. Timolol, a beta blocker used for glaucoma and high blood pressure, contains a thiazole ring that's a 5-membered ring with 2 nitrogens and a sulfur.
Okay, this brings us perfectly to that real-world structure elucidation example you mentioned, the green pepper flavor compound, a molecular detective story.
It really is a fantastic example of how chemists piece together a structure using different analytical techniques. They isolated this incredibly potent compound from green pepper oil.
First step, mass spec.
High-resolution mass spectrometry gave a very precise mass for the molecular ion, 166.1102. This allowed them to determine the exact molecular formula, C9H or HON2O. 9 carbons, 14 hydrogens, 2 nitrogens, 1 oxygen.
Still a lot of possibilities, though.
Definitely. Next, infrared IR spectroscopy. This looks for characteristic vibrations of functional groups. And the surprise here was what wasn't there. No OH stretch for an alcohol, no NH for an amine or amide, no strong CO for a ketone or aldehyde.
Ruling out many common groups.
Exactly. Then came the proton nuclear magnetic resonance, the 1H NMR. This tells you about the different types of hydrogen atoms and their neighbors.
And this started to reveal the structure.
It did. There were signals clearly indicating a branched alkyl chain, specifically an isobutyl group. A 6H doublet for 2 equivalent methyl groups, a 2H doublet for a CH2 group next to a CH, and a 1H multiplet for that CH group, Me2CH-CH2.
Okay, that accounts for C4H9.
Right. There was also a sharp 3-proton singlet around 3.9 ppm. That's a classic signature for a methoxy group, OCH3.
So C1H3O, we've used C5H12O. What's left from C9H14N2O?
We're left with C4H2N2. That has to be the core aromatic ring. The NMR also showed 2 more protons, way downfield around 7.8, 8.0 ppm, appearing as 2 distinct doublets.
Downfield means electron poor ring.
Definitely more electron poor than benzene or pyrrole. And crucially, the coupling constant between these 2 protons, the J value, was very small, only 2.4 hertz.
And that small coupling is the smoking gun.
It really is. A coupling that small between protons on an aromatic ring strongly suggests they are meta to each other, separated by 1 carbon. In a 6-membered ring with 2 nitrogens, this points directly towards a 1-3-4 arrangement, a pyrazine ring.
Ah, because in pyrazine, the 2 protons left would be meta-coupled.
Precisely. Putting all the pieces together, an isobutyl group, a methoxy group, and 2 metaprotons on a pyrazine ring. The structure had to be 2-isobutyl-3-methoxypyrazine.
Wow. All deduced from the spectra. So you said it was incredibly potent.
Unbelievably potent. The punchline is its smell threshold. Humans can detect this compound at concentrations as low as 2 parts per trillion in water. It's incredibly intense. The story goes that the lab where it was first identified had to be temporarily sealed off because the smell was so overpowering, even from minuscule amounts.
A fantastic illustration of how potent these molecules can be.
It really is. And it wraps up our tour nicely. We've seen just how diverse and important these aromatic heterocycles are. From simple pyridines and pyrroles to complex fused systems like purons and indols.
They're absolutely everywhere, from crucial medicines to the flavors that define our food.
Indeed, they play vital roles across chemistry and biology.
So as we wrap up, it really makes you wonder, doesn't it? Given the sheer number of possible heterocyclic structures out there and the profound impact of the ones we know, How much more undiscovered chemical or biological utility might still be hiding within these ring systems?
That's the provocative thought, isn't it? What potential lies untapped in structures we haven't even made or found yet? It really highlights the intricate dance of electrons and atoms that makes these molecules so fundamental and versatile.
They shape our world in countless ways, many we don't even notice day to day. Thank you for joining us on this deep dive.